Hi ladies, this is Blaufuss here. This is lesson 3.6 and it's about multiplying matrices. So with adding matrices, if you remember back to 3.5, adding matrices, we had to have the same dimensions. So the rows and columns had to be the same in order to add matrices because we were adding corresponding elements. So go back to 3.5 if you don't remember that, and just to refresh before you move on to the multiplying matrices, because this is a little more complicated and there's a few extra steps. But with multiplying matrices, you don't have to have the exact same dimensions, but with matrices A and B, the columns in A has to equal the rows in B. So if you look over here to the figure to the right on your note sheet, we still are identifying the dimensions of matrix as m by n. So A is going to be m by n, B is going to be m by n, but n in A has to equal m in B. So we're just saying that the columns in B has to be n. Okay, so that's saying that the rows in B has to be n instead of m. So we're saying that the columns in A has to be the same as the rows in B. If that's not true, then we cannot multiply these matrices together. Okay, so if we have a 2 by 3 matrix, we can multiply that by a 3 by 4 matrix because the columns in the first one are equal to the rows in the second one. But we cannot multiply a 2 by 3 matrix by a 2 by 3 matrix because the columns in the first matrix are not equal to the rows in the second matrix. Okay, so if that's not true, if the columns in the first are not equal to the rows in the second, then we cannot perform that operation of multiplication. So if it's not true, like in this example, we cannot do it, it's not defined. So this product matrix of the first and the second matrix, that would be undefined. So let's look at a couple examples. So here's our first matrix, here's our second matrix. So state whether the product AB is defined. So it's asking us, can we multiply these two matrices together? So we need the columns in the first to equal the rows in the second. 3 does not equal 4, so this is undefined. It cannot be done. In the second one, B, we have matrix A, 3 by 3, and matrix B, 3 by 2. We're looking for the columns in the first and the rows in the second. Can we do this? 3 is equal to 3. So this matrix is defined, and if it's defined, we're asked to give the dimensions. So if this matrix is defined, the dimensions are the rows in the first by the columns in the second. So this is defined as 3 by 2. So our product matrix AB is going to be 3 rows and 2 columns. So now that we know whether or not we can multiply matrices, we have to actually multiply matrices. So you have this key concept in your notebook. It says find the element in which the ith row and the jth column of the product matrix AB. Multiply each element in the ith row of A by the corresponding element in the jth column of B. Then add the products. Okay, so that's a lot of words. That's a very wordy definition, but we're going to do some practice problems so that you can understand this. But we're always going to start for both of them, both matrices. We're going to start in the first row, first column, in matrix B. We'll start in the first row, first column. So for A and B, matrix A and B, start in row 1, column 1. Now, for matrix A, though, it says find the elements in the ith row and jth column by multiplying each element in the ith row of A and the corresponding element in the jth column. So we are going to start at the first row, first column in both matrices, and then on matrix A, we're going to move across columns. And matrix B, we're going to move down. So we're going to move down rows. So that's why the number of columns in the first matrix has to equal the number of rows in the second. Okay, so here, matrix A, we're moving across. Matrix B, we're moving down. So our first term here is A, E, plus move across the row, B, and move down the column, G. Okay, and then our second term, because we're going to go back, first column, first row, A, F, we already did A times E, so now we're doing A times F plus B times H. So again, we're moving across row, down columns, and that gives us our first row, second column. And then for our second row, first column, we're going to start in the second row, first column. So second row, first column is C times E, and move across the row, across the columns here and down the rows here. So CE plus DG. And then lastly, CF, and we're moving across the columns and down the rows, CF plus DH. Now, if we had more columns and more rows, then we would just keep going across the columns in A and down the rows in D. So let's try one with actual numbers. It's a little bit easier to see when you're using real numbers. First question is, can we do this? So this is a 2 by 2 matrix. This is a 2 by 2 matrix. The columns in the first matrix equal the rows in the second. So we can do it. And then, secondly, to define our dimensions, we're going to end up with a 2 by 2 matrix. So AB is going to be a 2 by 2 matrix. So now let's actually sum this up. So I'm going to write it out the long way, and then we'll simplify it. But it's going to be a 2 by 2 matrix. So I have 2 rows and 2 columns. So in my first row, first column, I'm taking 1, times 3 plus negative 2 times 7. 1 times 3 plus negative 2 times 7. And I'm going to simplify this later, but for now, I'm just going to leave it like this. Okay, now my second column, I have 1 times negative 6 and 2 times negative 1. And I'm moving across rows in the first one and down columns. So 1 times negative 6 plus negative 2 times negative 1. And then in my second row, I'm going to move to my second row, which is 5 times 3 and negative 4 times 7. So 5 times 3 plus negative 4 times 7. And then lastly, I have 5 times negative 6 and negative 4 times negative 1. All right, so now if I simplify this, I've got 3, and we can simplify it even further after we do this, but this is my first element. And then my second element is negative 6 plus 2. Third element is 15 minus 28. And fourth element is negative 30 plus 4. So if I simplify this even further, I get negative 11, negative 4, negative 13, and negative 26. Okay, the next one is very similar, but it's not a perfect square. There's not 2 perfect square matrices, but we can still do it. This is a 3 by 2, and B is a 2 by 2. So those dimensions, the columns of the first and the rows of the second are the same. So the new dimensions, we're going to get a 3 by 2 matrix. So A times B is defined as a 3 by 2 matrix. So now let's actually do it. So again, we're going to move across columns here and down rows here. Okay, so now we have 3 rows in our first one. So we're going to have 3 rows in our final product matrix. Okay, so but we're going to start the same way. 6 times negative 1 plus 2, so 6 times negative 1 plus 2 times 2. And then our second term is 6 made a mistake. Let's go back one step. We need to go down columns, not, I went across for some reason. So we need to go down columns. So this should be, get my pen back, my pen. So we need to go across an A and down a B. So this should be 6 and -1 and 2 and 5, not 2 and 2. So this should be 2 times 5. Okay, for our second term, so we have 2 columns in this matrix. So our second term is 6 and 2. So 6 times 2 plus 2 and -2. Okay, and then our next term, so our second row, first column, is -1 and -1 plus 3 and 5. And then our second column is -1 and 2 and 3 and -2. So -1 times 2 plus 3 times -2. And then our last row, start with our last row here, 0 and -1, -4 and 5. 0, -1 plus -4 and 5. And then the very last one, our third row, second column. Third row, second column. 0 and 2 plus -4 and 2. And of course, now we can simplify this to our matrix to see our matrix. So if you look at these values in our matrix, just so you can kind of see some patterns, this -1 in our first column of our product matrix is our first column of B, and then the rows correspond to the rows for A. 6, -1, 0. Oops, let's do this in green. So here, 5 corresponds to this 5, and then 2, 3, and -4 correspond to the rows in the second column of A. And then we see times 2 times 2 times 2. That's where that comes from our matrix B in the second column. And then lastly, -2, -2, this should be -2. And this comes from our second column, second row of our second matrix. Okay, so now let's simplify this because there's like a lot of numbers that we have going on here. So Let's simplify it into one clean matrix. I'm going to have to do it a couple times, but let's get a little closer to simple. So 6 times -1, -6 plus 10 is our first element, working across 12 minus 4. Second row is 1 plus 15 and -2 minus 6. And then our last row, 0 minus 20 and 0 plus 8. So we can simplify this again by adding each of those terms to make up the element. So -6 plus 10 is 4, 1 plus 15, 16, -20. 12 minus 4 is 8, -2 minus 6 is -8, and 0 plus 8 is 8. So here is our final matrix. That's our solution. It's a 3x2 matrix. And this next one, please try on your own. And unpause for solution. And so here's the solution for this letter C. You have a 2x2 matrix. Can you multiply that by a 2x1? Yes, you can, because 2 columns in the first is equal to 2 rows in the second. So your dimensions of your new matrix are going to be 2x1. So you can pause this solution if you did not get 2469 as your 2x1 matrix. So that's your solution for this particular product matrix. And then here are some properties of matrix multiplication. Associated property of matrix multiplication. A times BC equals AB times C. Left distributive property. A times B, A times the group B plus C equals AB plus AC. And then right distributive property, if you're multiplying a matrix, adding a matrix and then multiplying by another matrix on the right, it's going to be different than if you're multiplying by another matrix on the left and then adding a group. So these are different because of how it's set up. Like a 2x3 matrix, you can multiply that by a 3x4 matrix. But you cannot multiply a 3x4 matrix by a 2x3. So we do not have the commutative property here with matrices. So we have a left distributive property and a right distributive property. So this is not the same. This one actually is undefined. And this one is defined as a 2x4 matrix. So the left distributive property is a matrix A times the sum of matrices B and C gives you AB plus AC. Right distributive property says the sum of AB times C equals AC plus BC. And then associative property of scalar multiplication, K times the group times the product matrix AB equals K times A times B, which also equals A times K times B. So this next example, which is the last one, and then you get to using your graphing calculator, which we'll do in class, and I'll do another short video if you need it, but it's also on your note sheet, so you should be able to work through those ones pretty simply. But in example 3, we're going to use matrices to calculate total cost. We actually have to set up some matrices, so we need to figure out what we're looking for first. So since the school stores from the middle school and the high school each submitted inventory list of the year, of sweatshirt, t-shirt, sweatshirt cost, t-shirt cost, and each pennant cost. So it's use matrix multiplication to find the total cost of the inventory for each school store. So we've got inventory here, and we want to know total, how much middle school has and how much high school has in dollars. So we have their inventory, we have how much each piece of inventory costs, so we need to set it up into two matrices where we can multiply those. So our first matrix is, we're going to look at inventory. So we're looking for total cost of the inventory. So let's first set up an inventory matrix. And we've got a few pieces. We've got middle school inventory. And we've got high school inventory. And within both of them, we have a sweatshirt, we have a t-shirt, and we have a pennant. Okay, so it says that the middle school has 61 sweatshirts, 63 t-shirts, and 74 pennants. And the high school has 58 sweatshirts, 71 t-shirts, and 92 pennants. Okay, now remember with multiplication, we have to have the same number of columns in matrix A as we do rows in matrix B. So since we're looking for matrix multiplication, and we know how much a sweatshirt costs, how much a t-shirt costs, and how much a pennant costs, those are now going to become our rows for our second matrix. So sweatshirt, t-shirt, and pennant. So a sweatshirt cost, and it's the same for both schools, so we don't need a middle school cost and a high school cost. If it wasn't the same for both schools, we would need a middle school t-shirt cost and a middle school sweatshirt cost, but it's the same for both schools. So $15 for a sweatshirt, $9 for a t-shirt, and $5 for a pennant. Now we're looking for total cost. So middle school sweatshirts times sweatshirts. Middle school t-shirts times t-shirt cost. Middle school pennants times pennant cost. Just a little bigger. So our total cost, well, first our matrices. We've got a 2x3 matrix and a 3x1. We can do that and multiply those together, and we're going to end up with a 2x1 matrix, which is pretty easy to work with. Okay, so let's actually say the cost equals, we're going to end up with 2 rows and 1 column, because we've got total middle school cost, this is middle school, this is high school, total middle school cost, and total high school cost. So middle school is 61 times 15, that's our sweatshirt cost, plus 63 times 9, that's our t-shirt cost, plus 74 times 5. That's our pennant cost. High school, our t-shirt cost is 58 times the cost of a t-shirt, which is 15, plus 71 times 9, which is the cost of a t-shirt, plus 92 pennants at $5 each. So if you do you evaluate these, and 61 times 15 plus 63 times 9 plus 74 times 5, you get a total middle school inventory cost of $18.52. 58 times 15 plus 71 times 9, that's 92 times 5. You get a total high school inventory cost of $1969. So our middle school has $1,852 in inventory. Our high school has $1,969 of inventory. Okay, I know this video is a little long. I'm going to do a separate video that talks about calculator use. So please jot down any questions you have, and we can go over those in class. Thanks.